Okay, welcome back to my channel everyone. My name is Ansar, your helping hand, and in today's video we're going to be going through another IFoA exam question, specifically one that has to do with the central limit theorem. Okay, so this question comes from the 2011 paper, and it's the April paper, and it's question 2. So as usual, I'm going to show you the question, let you pause the video, and attempt it on your own, and then come back for the answer. Okay, so the question reads as follows. A random sample of size n equals 36 has a sample standard deviation s equals 7. Calculate approximately the probability that the mean of the sample is greater than 44.5 when the mean of the population mu is equal to 42. Okay, so pause the video and attempt it on your own and then come back. Just a quick hint or little explanation. Whenever we say a random sample, what that basically means is that we're taking independent samples, right? That's one of the criteria for a random sample, is that it's independent from each other, and also that all the samples that you're taking are identically distributed. So a random sample just means IID, essentially. Okay, so pause the video, attempt it on your own, and then come back for the answer. Okay, so I'm assuming you have completed or attempted to try the question on your own. So essentially, this is a typical central limit question, and the reason that it's a typical central limit question is because, we have a random sample, right? We have IID random variables, essentially, and we're not told what the distribution of our IID random variables are. We're not told anything about this distribution, and we're asked to calculate an approximate probability on some statistic of the random variables. Specifically, we're asked to calculate a statistic on the sample mean. So other times they can ask you to calculate a statistic on the sample sum, essentially. So it's just good to kind of go over what the central limit theorem says. So the central limit theorem says that the limit as n goes to infinity of root n x bar minus mu over sigma is approximately normal 0, 1. So in this case, we basically have most of the information we need in this for the statistic. And then there's this other kind of thing that we need to just address, which is that obviously we don't have infinitely many things. So we don't have an exact normal distribution when we take this particular statistic, but as n gets bigger and bigger and bigger, this is going to look more approximately like a normal. That's where the approximation comes in. The other part of the approximation is the fact that we don't actually know what sigma is, that we haven't been given what sigma is. They tell us what mu is, so we do have mu, but we don't have what sigma is. We only have s. Now, if you're not given any other information about your random variables distribution, so if we were not told that our random sample, we're taking a random sample where our samples have a gamma distribution or an exponential distribution or a Poisson distribution, we can't figure out what sigma is. We can't calculate what sigma is. And if we're not trying to make an inference about sigma, right, we're trying to make an inference about our sample mean, we need to know what sigma is, or we need to have an estimation of what we think sigma might be. And this is where your approximation comes in as well, which is that basically, essentially what we're trying to say is that our s squared is approximately equal to our sigma squared, and so therefore our s is approximately equal to our sigma. And this is where your approximation is also coming in on top of the central limit theorem thing, where we're saying, okay, as n gets bigger and bigger, the statistic looks approximately normal. We're also approximating our value of sigma because we don't actually know it. So that means that we can therefore say that the square root of our n, which is 36, right, multiplied by x bar minus our mu, which is 42, over our population standard deviation, but we don't have that. We're approximating it using our sample standard deviation, which is 7, right, that's all in the question, is approximately normal 0, 1. And approximately comes in because we're using the central limit theorem and we're saying, okay, maybe n is big enough for this approximation to be useful, right? So that's the first approximation that we can do, right? The other approximation that we can do is we can make an assumption about the distribution of our data. So we haven't been given any information about our distribution, about the distribution of the data, but if we assume, right, and this is now kind of part of where your judgment call comes in an exam question, depending on how you want to answer it. If you can write down an assumption. Well, I'm not entirely sure if this works for Math Stats 214, but in a lot of your actuarial exams, if you make an assumption about something and you put the assumption down, a lot of the times the markers will mark with your assumption being held true if you can justify it for some reason, or if it's not an unreasonable assumption. So if we're assuming that our data is normally distributed, right? So this is our assumption that we're putting down on the paper. So we can now use the assumption that we've made. So if we assume that our data is normally distributed, and our justification for this could be any number of reasons, right? We don't really know much about our data at the moment, but if we knew a bit more, we could say, okay, this is actually possibly a normal distribution. Alternatively, you can just say that it's normally distributed and use the result from there. So if we do have a normally distributed data, then we know what square root of n multiplied by x bar minus mu over s, right? Because we're using s, we know that this has a t distribution with n minus 1 degrees of freedom. So we could say that the square root of 36 multiplied by x bar minus 42 over 7 has a t distribution with 35 degrees of freedom. So these are the two approximations that you can use to calculate your approximate probability. Either a t distribution if you're assuming that your data is normally distributed, or you can use a normal distribution if you're just using the central limit theorem. And the reason you can just use a normal distribution in the central limit case is because what we're doing with the central limit theorem is that we're taking the standardized form of our sample mean, and the central limit theorem says that as n gets larger and larger and larger, that standardized sample mean will look normal. So basically, that our approximation comes in here, where we're saying, okay, we're saying n is large enough for this statistic or the standardized sample mean to look approximately normal when we're approximating our sigma with our s as well. And here the approximation comes in when we're assuming that it's normally distributed, and therefore we can use this result, which is an exact result if you have normally distributed data. I'm going to use the central limit theorem version of this, not the t distribution, but we can compare the answers later. So the question asks us to calculate the probability that our sample mean is greater than 44.5. So this is the same thing, right? Or this is approximately, right? When we're using the approximation that x bar is somehow normal, right, from the central limit theorem, we can standardize our x bar in the correct way. So we can standardize it by taking x n bar, minusing our mean, which is 42, multiplying by the square root of our n, which is the square root of 36. So I'm just going to put a 6 there, and dividing by usually our population standard deviation, but we're approximating that with our sample standard deviation, which is 7. That is, that should be greater than, and we do the same thing to the 45. So we'll get 44.5 minus 42 multiplied by 6 over 7. Now that's just equal to the probability that some z random variable, where z is standard normal, right? Because that's what we're saying, this is approximately equal to a standard normal random variable, that's, I keep on writing the greater than or equal to, sorry, that's greater than, if we calculate the value of this particular statistic, you'll see that it's equal to 2.143. And if you go and calculate the probability using however you calculate your normal probabilities, you'll see that this comes out to 0.016, right? So that's using our central limit theorem approximation. Just out of interest, if you use the assumption that your data is normal, right? If you use the assumption that your data is normal, then what you'll have is that the probability that the square root of 36, which is just equal to 6, multiplied by x bar minus 42 over 7 is greater than or equal to 44.5 minus 42 multiplied by 6 over 7, right? That's the probability that some t is greater than the same value, 2.143, where t is a t distribution with 35 degrees of freedom. And you can go and work this probability out as well. And this will come out to 0.0195, right? So we can see that almost up until 2 decimal places, we have the same answer. Obviously, if we round this will be rounded up, and that won't be rounded up, but obviously this also has more things, so it might have been rounded up. It doesn't really matter. All we know is that these two values are close to each other because the t distribution and the z distribution look similar, but this probability, this approximate probability, is using the assumption that our data is normal, and this approximate probability is not using that assumption, but it is approximating our standard deviation, our population standard deviation with our sample standard deviation, but it is also using the central limit theorem. So it kind of depends on how you want to answer your question. They haven't given you any particular direction, so they haven't said using the central limit theorem, they just said calculate approximately. So these are two valid approximations depending on how many assumptions you want to place on your data. Okay, so that's the end of this video. Please don't forget to like and subscribe, comment if you have any questions or requests, and yeah, I'll see you in the next video. Bye!